Hopefully the sound will be working its way back out. Good evening, everyone. For the 097 people, I'm throwing out some people have asked me about the worksheets in the 097 class that weren't handed in before break. I'm sending out electronic copies of those so you can attach your answers onto them. I am still getting pictures from people that are not legible on the phone. Doing my best with those. Outside of that, all the homework is posted for this class. I took the Chapter 4 test, so that will be going live tonight, and I'll make a copy of it. That has practice questions on it. I have to do that. So that's the things that I'm doing tonight when I'm done from here. But I should have all the assignments up before tomorrow is old. I've gotten all my classes lined up, made sure the lectures were in step. We weren't losing in any information, and everyone just vanished. Huh. Let me see if I can. Since I didn't put that in there. I had everyone in there and then they all vanished, so hopefully it's a small stream problem. Let's see here. Do I have sound going out here? Yeah, I got sound going out here. Alright, so all the assignments should be up and running towards the end of the week. So today I'm going to talk about asymptotic behavior of rational functions for the first part of things. And then for the second part of things, I want to be looking at domains and how we can do function algebra. Hey, Emily. So we'll work on rational functions for the first part and work our way to function algebra on the second part. Where function algebra is what we'll be chewing our way through. We need it to really develop the work with exponential functions, which are the bread and butter. I keep repeating this in a couple different classes, so if I am a broken record, probably the best form of mathematics for physical sciences or any science at all are differential equations. And differential equations, their answers come in the one of the easiest functions to make an answer for them are exponential functions. And so learning how to use exponential functions is kind of the crux of any lower mathematics, because the tool that makes solutions for problems puts exponential functions. There's another tool where you can make any function into a polynomial, which is why a lot of these courses kind of have a big chunk on polynomials and a big chunk on exponentials. So we're going to be dealing with the tools we need to really talk about exponentials in the second half of things. But for now, we're going to look at rational functions and asymptotic behavior. So we started classifying rational functions, and I want to make sure that these classifications we can start using with and looking at the asymptotes. So we defined a rational function as some f of x that has two distinct parts and both the numerator was a polynomial and the denominator was a polynomial, such that this denominator could not equal 0. Now, when we do this, certain things can happen. If there are areas in the domain where the denominator can equal 0, they can make holes in the graph. Places where the function doesn't exist. Because by definition, division by 0 is not defined. If I take something and divide it into 0 parts, that has no meaning, both in English and mathematically. So we avoid having functions that have solutions. or not solutions that have input that would cause this lack of definition to happen. And we called this a domain restriction. And so when we see this play through on rational functions where somewhere the denominator might end up equaling 0, we get what's called asymptotes. And so I guess the base function that we could look at would be 1 over x, where x cannot equal 0. So I'm going to pull that up in my graph here. All right, graphs are up. Let me close these guys out. We'll come back to those. And so we'll look at the function 1 over x. And just to show the asymptote, I'll show the green line of x equaling 0. And so we have the blue line being our function 1 over x. It's a rational function with a constant polynomial in the numerator and a linear first degree polynomial in the denominator. The linear portion of this cannot equal 0. What ends up happening is there's a hole whenever x equals 0, and this function approaches this vertical line but never touches it. And so this is called a vertical asymptote. So let us define that vertical asymptote. Let's give a definition of what a vertical asymptote is, because our job is to find these. I'm doing a little review from what we ended talking about, but we're going to use these definitions in a little more detail. So vertical asymptote. And the definition of a vertical asymptote is it is a line of x equals some value k. Such that some function f of x approaches either infinity or f of x approaches negative infinity as the value of x gets closer and closer to k. So let me put these definitions down here. Whoops, wrong thing. So vertical asymptote is a line, hey, x equals k. As the function of x, or as the value of x gets closer to k, the function is either going to zoom off to infinity or negative infinity. And so that's what this vertical asymptote definition does for us. And we should be able to see that here on our graph, that as I get closer to x equaling 0, the value that spits out of my function zooms off towards negative infinity and positive infinity. We can never get to infinity, so we can never get to where we're touching this asymptote. And so this is a vertical asymptote because it is a vertical line that the function approaches but doesn't touch in its behavior as it gets closer to this value. And so we're going to have, let me get back to the blackboard here. This definition of vertical asymptote is a line x equals k such that our function approaches infinity or negative infinity when x approaches k from either the right or the left, right? If we come from the positive side and or the negative side, it approaches these things in such a way that the values can shoot into opposite infinities. They can shoot towards the same infinity or they can shoot towards the opposite infinity. And 1 over x, as I'll zoom back to this graph here, you'll see a lot of back and forth between the graph here, but 1 over x, if I'm approaching x from the negative side, it goes off towards negative infinity. If I'm approaching x from the positive side, it goes off towards positive infinity. That's not always the case. The function itself will determine that. So for example, if I just make this into an x squared, I still have an asymptote at x equals 0, but now if I approach x if I approach 0 from the negative side, it goes towards positive infinity. And if I approach 0 from the positive side, it still goes to positive infinity. And so part of this behavior is what we want to define and look at. All right. And so we have a vertical asymptote, and we're going to work on finding the asymptote. But we also have asymptotic behavior that approaches other values. And let's look at another function here. I'm going to find that we're going to be back and forth with graphs a lot as we look at these behaviors. That's why I hand out things on about Desmos, because I find it's a good utility to graph the things we're looking at and to see what the behavior is. Whoops. Of course, it helps if I can type today. So I'm going to make my rational function to look like this. And there are no vertical asymptotes. There's nowhere the denominator can equal 0. But if I zoom really far away from this function, the value of the function, let me turn this into a small dotted line here. Make it smaller. Nope. The value of this function in its big behavior approaches a horizontal line. And so let's zoom in on it here. It shoots above the line here, but as I go off towards infinity, it gets closer and closer and closer to the line. Right? See how it's running towards that line, getting closer the larger and larger my x values get. Go back to the center here. Sorry about the mouse sounds. And the same thing happens if I shoot off towards negative infinity. I get closer and closer to that line. And so there's a horizontal line that my function can be bounded by. And that's going to be called a horizontal asymptote. And this is an example of a horizontal asymptote. In fact, it's at 3. Y equals 3. So I think that's going to be the other thing we're going to define here as a horizontal asymptote. And so let me change colors. I'll go with ugly green. Horizontal asymptote. So we have a horizontal asymptote, which is a line y equals some value b. All right, so x equals is a vertical line, y equals is a horizontal line. That my function approaches the value b. Gets closer and closer to the value of b as x approaches positive infinity or x goes off to negative infinity. And so that's the definition we're going to use. It talks about the behavior of the function when it's as far away from 0 as possible, and that there is a tendency for this function to approach a horizontal line. Now with the previous function, it was the tendency of the function as we got closer and closer to a value, right? And so vertical asymptotes are the behavior when you get close to a particular x value, and horizontal asymptotes are the behavior when you go off towards infinity, when you're getting towards infinity. And so if we look back at our graph for this here, right, we can see this function has some interesting behavior near 0, but in the long run, it's as good as being 3. And that's kind of the value of understanding asymptotic behavior, is you can talk about, you can simplify what you're talking about. You can say, well, if I'm really, really close to the middle of this function, and there's some interesting stuff going on, I have to pay attention to it. But if I have a really, really large value of x, I can just treat it like that, like the horizontal asymptote. And we'll define out that when we look to find those. I want to define the things, and then we'll hunt them down. Well, I guess there's going to be another type of line that we can get here. And let me find a nice example of one of these. I had one the other day. And I just want to make sure I get, yep. Where did I put it? I think I put it here. Hold on, let me put this up on the graph here. Typing it into the graph. I'll turn the graph on in a second here. I need to realize it's off. Just give me 1 second. What's the denominator? X squared minus 3x plus 2. Trying to get my graph to work here. Now, we'll use this as a representation. I have it here. I know it has one. So let me switch over to the graph here. There we go. We got a graph going on. Let me turn this off for right now. We'll get in the details. Whoops. Alright, so here we have a function x cubed minus 2x plus 1 divided by x squared minus 3x plus 2. Now, the denominator does have places where it can't equal 0, and that's right here. And so there is a vertical asymptote at this 0. And when we go far away, this function tends to look like a slanted line. You see the slanted line here? Right? That the function approaches. And so what we want to be able to do is figure out what that slanted line is. And that's going to be a slant asymptote, or a slanted asymptote. And so we have these different types of asymptotes that we can find. And the definition for a slant asymptote, let me go back to the blackboard here. I'm just happy that the blackboard's changing back and forth between the graph a little bit closely. A slant asymptote is some line y equals mx plus b that f of x approaches that mx plus b as x goes off towards infinity or x goes off to negative infinity. And so there are three types of lines our functions can approach. They can approach pure vertical lines, they can approach pure horizontal lines, or any of the lines we've studied before. And so our job is going to be finding these and finding the values of these, because they tell us a lot about our functions and what our rational functions and what they can be doing. So I'm going to start, we're going to start and we're going to look at a rational function that will have some asymptotic behavior. And we're going to look at finding that asymptotic behavior and what it means. So let's find a vertical asymptote, and we'll start with finding a vertical asymptote. So to find a vertical asymptote, we first write the function in its lowest terms. So if we have some p of x over q of x, we list all the factors of px and all the factors of qx, and we cancel any factors that are the same. So for example, if I had the fraction 3 times 6, well, that's 1 times 3 over 1 times 2 times 3. The 3's cancel. And in simplified forms, that's 1/2. Well, let's look at a function that isn't numbers, and we'll simplify those. But once we write them in lowest terms, then we set the q of x equal to 0, and these values are the vertical asymptotes. It's the places where the function is trying to divide by 0, and so we can't have those. So let's look at one of these functions that we should simplify, and I'll show the difference between simplifying and not simplifying. And I'll go to h of x is x cubed minus 2x squared plus 1 over x squared minus 3x plus 2. Now, the original denominator can be factored to x minus 2 times x minus 1. So my domain of my function has two values it can't be. X cannot equal 1, and x cannot equal 2. All right, x squared minus 2x minus 1 and minus 2 is positive 2. Yep. Okay. And so we need to factor the top fraction. So I'm looking for any zeros on this that might help me factor this. I think probably the easiest way to look at this would be, let's see, if I put 1 in there, I get 1 cubed minus 2 plus 1, and so it would be 1, right? Well, let's do that. Let's factor this. Let's use our rules. So I want to factor this, so I want to divide it down. So my rational root test says I can either have plus or minus 1 as a rational root, right? So for the p of x equal to x cubed minus 2x squared plus 1, my rational root test says I have a rational root of 1 or 1. So I'm going to use my remainder theorem, and I'm going to put a positive 1 in there. So positive 1 cubed minus 2 times positive 1 squared plus 1. So that's 1 minus 2 plus 1, or 0. So positive 1 is a root, which means x minus 1 is a factor of the upstairs. That was what we've been studying the first couple sections of chapter 4, is how to find these roots, where they're going to come in useful for us here. So I'm going to use my division. I'm going to put my coefficient of 1, negative 2, 0, and 1, and I'm going to use positive 1. So I bring down my 1, multiply, add, and using my synthetic division, I get that my other factor is x squared minus x minus 1. Looks like I ran out of room down here on the bottom. See if I can add some more space here. View, edit, image, properties, scale image to new size, resize canvas. So I want to add go. Sorry, this is taking me a second. Didn't mean to run out of space there. There we go. And so I can rewrite this x cubed minus 2x squared plus 1 as x minus 1 times x squared minus x minus 1 all over, what did I have on the bottom? X minus 1 and x minus 2. But notice these two are going to cancel. So in simplified terms, that's the rational polynomial I'm looking at. X squared minus x minus 1 over x minus 2. All right, I'm going to put both of these up on the graphing software so that we can look at them and see what they do. And so I have the first one up here. And what I'm going to do is I'm going to put the simplified form of it in. So let's zoom in somewhere near 0. Just that'll be good enough for me. And then what did we say was upstairs? It was x squared minus x minus 1 divided by x minus 2. No, I got something small off, probably off by a sign. X squared minus x minus 1 over x minus 2. What did I... Negative 1, negative 1, negative 1. X minus 1, x minus 1. I typed something wrong here. Let's see. X cubed minus 2x plus 1 over x squared minus 3x plus 2. X squared minus x over... What did I type wrong? Well, I did this perfectly fine earlier. Let me go back and look for a sign error. This is usually a sign of a sign error. As I should have an asymptote at negative 1. Let's go back here. Make sure I wrote these in. X cubed minus 2x squared plus 1 over x squared minus 3x plus 2. That's right. Are those factors? That gives me x squared minus 2x minus 3x plus 2. Those are the correct factors. I put x minus 1 in there as a root of 1. That gives me, let's do my synthetic division. 1 does cancel out. I get 1. Multiply back through, I add. That's negative 1. Multiply back through, that's negative 1, negative 1. Add, that's good. That's x squared minus x minus 1. Those cancel out. Squared minus x minus 2. Let's remultiply. I get x cubed. I hate making a sign error, and I know I made one right now. X cubed minus x squared minus x minus x squared, that's 2x squared, plus x, that cancels out the x, plus 1. That works up there. All right, what did I do up here? Sorry, I went through the equation and redivided, and I'm looking for a sign error on this because these graphs should do each other exactly the same. Ah, that's what it is. I forgot to enter the x squared here. It was a typo there. I do apologize. I knew there was an error and it was small, and so I double checked all the work there. So notice these graphs overlap each other. They're the same representation of the same thing. Just one is in simplified form. And so I had forgotten to type the x squared here, which is why it looked differently. Now notice there is an asymptote at y, or x equals 2. There's a vertical asymptote at x equals 2 because the denominator of the simplified form of the fraction cannot have a value at x equals 2, and it makes this asymptote where it runs off towards negative infinity and infinity. But our domain of the function still is limited by there's a point here where at 1, 1 that doesn't exist. It's a hole. It's a hole in the function because we can't have a value of 1 because that makes the initial function 0. And so we have a couple points of interest on this. Our asymptote is defined by the simplified version of the function. but our domain restrictions are defined by the original form of the function. And so this graph goes, and there's a hole right there that we have to jump over. Sounded like the floorboards just about went there. And then when we get to where x equals 2, there is the asymptotical that comes about. And so when we go to find vertical asymptotes, we have to reduce our fraction. We have to factor the numerator and the denominator and cancel any factors that are in the upstairs and the downstairs. Then the only things left on the bottom are the actual asymptotes. Right. I didn't even notice I didn't have the square in there. So I went back and double checked all of these really quick, and my typo was in the software. I forgot the square, but we fixed it. It does what it can, and that's a vertical asymptote. All right, so vertical asymptotes aren't too bad to find. I mean, we've been spending a week and a half, 2 weeks, finding the roots of polynomials, and the roots of the polynomials are the driving thing here. We find the roots of the upstairs and the roots of the downstairs, and the roots of the downstairs are domain restrictions. Our function can't exist there. When we cancel everything out, what is ever left downstairs are our asymptotes. If I try to sum that up, all right, let me scroll up here to get some more space, and we'll look at, well, okay, finding vertical asymptotes is all finding the roots. Let's look at horizontal asymptotes then, and I think I'll switch to sky blue. I really like the sky blue on this. So horizontal asymptotes are found in 3 different rules. And so the first one is if the degree, and what we end up doing is we compare the degree of the numerator to the degree of the denominator, right? And so I think I'll call this n sub p for upstairs and n sub q downstairs. Because remember, n was just why I'm using this nomenclature. When we defined any polynomial, we said x to the a sub n, x to the n, plus a x n minus 1, all the way down, n minus 1. Thank you. There we go. Horizontal asymptotes. Thank you, Eric, and thank you for using that. I mean, it's been sticking on me the last couple of classes, and that's been ticking me off. A x sub n is how we defined our polynomial. And we said the degree of the polynomial was at whatever the highest power of. All right, so the rules that we have for this compare the degrees. And so the first rule is if the degree n sub p, the degree of the numerator, the upstairs, is less than the degree n sub q, or the downstairs, then y equals 0 is the horizontal asymptote. So no matter what numbers or everything I have in there, if the degree upstairs is less than the degree downstairs, y equals 0 is the horizontal asymptote. So let's make one here. Let's see if I can go back to the graph on you here. Oh, switched. It's a good start. Now I have to switch over to I'm on the graph. So I will make a function. I'll make the degree upstairs. Let's see. I'll do 752 x to the third minus 562 x squared plus 20x minus 12. That's my upstairs. And then my downstairs, I'm going to have 0.1 x to the fourth minus 3x cubed plus, whoops, why does it keep doing that? And I'm trying to be overly dramatic with big numbers here. Plus 2x minus 1. And so I've got this weird function that's actually doing a lot near 0, right? Lots happening near 0 here. It's bouncing all around because it has these big numbers that are zooming it out. But as I zoom away, it starts approaching y equals 0. No matter what those big numbers are doing really close to x and causing this to bounce, or really close to 0, causing this to bounce around, as x gets larger and larger, y approaches 0. So let me make smaller ones here so we can see some stuff happening for us here. So I'll bring these down, make these numbers much smaller. And so there we have all this behavior happening close to 0, but in the long run, this fights its way back to y equals 0. And all that matters for that is the power of the leading terms. The idea behind the power of the leading terms working is if I am near infinity, right? So let's say I have a billion, right? Well, 12 compared to a billion doesn't matter. So I don't have to look at that thing. So I'll take the 12 out. And 1 near a billion doesn't matter. So I'll take that out. Right? And I still get the general graph. Things happening near 0 have changed a little bit. But in the long run, it ends up being the same. Well, a billion cubed is a lot bigger than a billion. So that doesn't matter to a billion cubed. And that doesn't matter to a billion cubed. In the long run, my graph is still doing the same. And as I get bigger and bigger and x gets bigger and bigger, the only things that have value compared to the other terms are the leading terms. And the leading terms, as we get closer to infinity, fill out this shape. And this shape is 1 over x. Or 1 over x squared, or 1 over whatever the power difference is. But in the end, the lines approach y equals 0. No matter what the power difference is here, as long as the bottom denominator, notice I put in a 4, and it looks like this. If I put in a 5 downstairs, it looks like this. But still, overall, the big behavior of this function is to approach 0. Approach y equals 0. Okay, I'm going to try to go back to the blackboard here. You guys scream out if you don't see it, since I keep you guys off to the side. So the only thing we compare for the first one is if my degree upstairs is less than the degree downstairs, my horizontal asymptote is going to be y equals 0. All right, well, if the degree of the upstairs is equal to the degree downstairs, they're exactly the same, and the big behavior is all that matters, then in the leading coefficients, a sub n, x sub n, and so on upstairs, and b sub n, x sub n, so on downstairs, right? We're talking about a polynomial, but if these two are exactly the same, the only thing that matters are these things, the leading coefficients. And this will approach the line y equals a sub n over b sub n. If they're exactly the same, it'll approach a number. And that number, that isn't zero, that is the leading coefficients. So I'm going to show an example of this. And these rules are on 327 of your book for finding horizontal asymptotes. I really like showing the examples because they're fairly intuitive, or it's fairly intuitive for the rules to stick when you see them. Yeah, there's the words I wanted. All right, so we'll go back to this graph. And 3x squared minus 4x plus 2 all over let me actually change this. I want to make this 9x squared over 3x squared minus 2x plus 1. We'll zoom back into this. And so notice that the leading coefficient upstairs is 9, and the leading coefficient downstairs is 3. And this function approaches 9 divided by 3, or 3, for its big term behavior. And what's happening, again, is the same kind of idea. As x gets bigger and bigger and bigger, right? If I put 1 billion in there, 1 billion squared times 9 minus 4 times 1 billion plus 2. Well, that 2 doesn't matter. And 1 billion squared compared to 1 billion, that 4x doesn't matter. So the only thing that matters is the 9 billion squared up top, right? Well, downstairs, the same thing happens, and the only thing that matters is the 3 billion squared. Well, the billion squareds are canceling each other out at about the same rate, leaving me with the 9 over 3. And so as these functions as the x values get bigger in absolute value, the leading term defines what's happening. I could make another leading term here. I'll put 15x cubed minus 9x squared, and down below I'll put 5x cubed plus this. Now notice the leading coefficients here are 15 and 5. So if I divide 15 by 5, I get 3. And if I zoom out, let me put a y equals 3 in here so we can see it. As this gets further and further out towards infinity, it approaches the line y equals 3. And so the leading coefficients take over when the value of x gets really, really large. This is a concept that's going to come back to you as you study the pre-calc and the calculus material. That what happens as you go towards infinity, or as you get really close to dividing by 0. And the asymptotic behavior is how we first see this. And calculus kind of helps us mathematically deal with it. But right now we're seeing this and moving on the functions. And so that secondary rule, I'll switch back to the blackboard and see if it works, tells me if the degrees are exactly the same, then in my horizontal asymptote is the ratio of the leading coefficients. And then in the last possibility we have is if the degree of the upstairs is bigger than the degree of the downstairs. And if the degree of the upstairs is bigger than the degree of downstairs, you get no horizontal asymptote. So we have these things that happen with our functions. They shoot off towards infinity. in their y values when they get close to dividing by 0. And we call those vertical asymptotes. When our function itself gets out towards infinity and it approaches one value, those are horizontal asymptotes. And the degrees of the function are really important in the horizontal asymptotes. All right, the last asymptotic behavior I want to look at is the slant asymptote, and what happens when the lines approach a slant. And I think I'm going to go back to the first function that we had that had a slant asymptote on it, and I'll look at a couple examples of those. So we have 3 types of asymptotes, and we're going to look at an example of each. I'm going to use obnoxious yellow. I don't think I've used enough obnoxious yellow today. And we'll do slant asymptotes. And then, am I on the blackboard? Yes, the blackboard is showing. All right. Got 3 places I'm checking these streams and making sure everything shows on them. Coming across. I had twice now. The streams themselves have died on me. And I think it's my router, just with all the traffic on it lately. So I've been making sure I'm rebooting that in the evenings. And then I've been having an issue where this software is sticking when I go to switch between windows. And I still haven't figured out what does it because it's not consistent yet. So I've been making sure I comment on it and then jump back to you guys about looking at you guys off on the side to make sure it happens coming across. So thank you for letting me know that. All right, so slant asymptotes. We can talk about the division that happens giving us a quotient plus a remainder over our divisor. And one of the things that happens is this divisor is going to have our x value in it. So as we get towards this x value, as this gets closer and closer to infinity, this goes away because we're dividing by a bigger and bigger and bigger number, right? If we can pretend that this is some, I'll just say for right now, this is some, we'll call it the Q function, right? And this is an R function, and this is a divisor function. And you get the words out of here. And they're all having x in them. Well, as x gets bigger, as we go out towards infinity, as x approaches infinity, and this value gets larger and larger and larger and larger, because this is a polynomial, this value is going to get larger. It's either going to get closer to negative infinity or closer to positive infinity. It's going to zoom out. I'm dividing this r by a bigger and bigger number. And so you can think of, if I divide 1 by 1, I get 1. If I divide 1 by 10, I get 0.1. If I divide 1 by 100, I get 0.01. I get smaller and smaller. This gets closer to 0. So much so that it goes away, leaving me with this. And so if the quotient is in the form of mx plus b, then that's going to be my slant function. And so when we have slant asymptotes, it's the quotient that tells us the line of the asymptote. Quotients and dividers, quotients and divisors, quotients and divisors. I've got to do polynomial division here. And due to the nature of the polynomials I'm dividing, it's most likely going to be long division, not synthetic division. So let's look at the function that I started with here when I showed you a slant asymptote. I want to make sure. Oh, didn't mean to do that. There we go. Getting bigger, getting smaller, getting bigger, getting smaller. There we go. A function I want to look at to see if it has a slant asymptote was our function. I think I have it down here. I'm sliding down for it. Yes. This x cubed minus 2x squared plus 1, x squared minus 3x plus 2. So let me plop this onto my graph. And make sure I type in the squared bit. Remember, I didn't type in the squared bit last time. Cubed minus 2x squared gotta find a way to add audio to this. I've tried other apps and the quality of the screen sharing on them are not that well. Zoom meetings get too chaotic. I gotta find some way I can just hear you mumbling in the background. Usually ends up being everyone just eating food while you babble. You guys are good. You're answering questions at least, or asking questions at least. So this has a slant asymptote to it. So I want to find the equation for the line for it. So what we're going to do is we're going to use long division on this to find it. And so this is the division we're going to do. So let me get back to that. There we go. Now I'm going to scroll all the way down here and set up my long division. Make sure, yep, I have enough space. Good. All right, so I'm going to divide x cubed minus 2x squared. I have nothing in the x term, but I've got to hold place for it. Plus 1. I'm going to divide all of that by x squared minus 3x plus 2. So x squared goes into x cubed x times, right? Our leading term determines what we need, and then I multiply this back through. So that gives me x cubed minus 3x squared plus 2x. I change my signs, and then I'll add. So these should cancel out if I've done my job right, and this gives me a positive x squared. This gives me a negative 2x plus 1. My new leading terms tell me what's going on. And that's a 1. So I'll multiply this by 1. So x squared minus 3x plus 2. I'll change my signs. These cancel. That gives me a positive x minus 1. This part here was my quotient, and this is my remainder. So this is my slant asymptote, x plus 1. So let's look at that on the graph. And that line x plus 1 is what our functions approach when they get out towards infinity. And these are all the different asymptotic behaviors we can have. They can stack up on our functions, and they can work our way through the functions in different ways. And I want to look at a couple examples, 2 examples, and then we'll take a short break, and we'll come back and look at more function algebra, since this is in itself function algebra. I want to find one that has both. Got like 8 that I've looked at in the course of things here. All right, I'm going to look at a slant asymptote all slant and vertical asymptotes. So I'm going to do this for, there we go. Are we still on the graph here? Let's switch over to the blackboard. So it depends on what you mean by solving, Eric. So what we want to find, so Eric asked the question, would we write the remainder and divisor when solving? Let me pull back to this on the blackboard here. So x plus 1 plus x minus 1 over x squared minus 3x is the answer to that division of what the polynomial division is doing. Now, for us, we don't need to reduce it to this form. We don't need to pull out the division to get anything useful from it. Leaving this in the form, I'm going to have to scroll up to the red here. This form here is okay. This is an okay way of talking about this polynomial. What we're doing by manipulating it like this is finding something that describes it for us. And so this part here, when the function gets out towards infinity, it approaches 0. Doesn't have much value for us. But knowing this part here, let me go back to the graph again, gives us that line that it's approaching. So I want to stress just in the word choice here, we're not solving the division, but we're describing the graph or the behavior of this function. And particularly we're describing what it does as it goes off towards infinity. And look at it this way. I hope you can see the function up here in the corner. Let's say this is something that came out of a measurement I did. I had an input and output function and they were divided. And this was something in reality that I had to work with. Now I have 2 problems with division by 0 in this. And those were the domain restrictions we found originally. Right? This couldn't be x cannot equal 1, which is this point here on here. And x couldn't equal 2, which gives it a vertical asymptote. Vertical asymptote at 2. But let's say for some reason, whatever I'm doing, I'm not putting in anything less than 10 on it. Right? Let's say it's some output that's measuring the value I have for the money I spend. And I'm not going to spend less than $10. Right? Well, as I get further and further away, it's better to describe this function as the line x plus 1. It's a much easier description of what's going on with it. And so if I were putting in $150, $300, $400, x plus 1 would be a much better description than having to put 300 or 400 into this whole thing and do 300 cubed minus 2 times 100 squared plus 1 divided by 100 squared minus 3 times 100 plus 2. And so when we talk about these long-term behaviors and the things we get out of them, we're hoping for a way to reduce what we're talking about. It's not the same as an answer. Right? I know I'm kind of splitting on word choice there, but these behaviors we're talking about are a more general description of what the function is doing. Almost like a zoomed out view, which is why I'm zooming in and out on the graphs. And how we're using a function really determines what parts of it we use. If this function is something that really matters for me from the vertical asymptote to 6, right? If the values I'm putting in, I can put in 2.01 or 4.04. If the domain of what I'm doing is in this small area here, then I have to use this function coming out of here. But if the large values matter and I know it's approaching a slant asymptote, then I do the division and I get the quotient. The remainder in the divisor doesn't give me any more information at that large scale. In fact, they make the calculation a little bit harder for me. So that's the best I can say that. I like, in general, when I do my divisions, I usually put this off somewhere on the side because I might end up needing it again. But for what we're doing, the quotient part is the part that gives us the information. Hope that answered that. I know it's a subtle thing, and I think doing a couple problems will show. All right, let's look through. I want to find one that is, I just had it, and I'll put it here. We should be back on the blackboard, I hope. Yep, we're back on the blackboard. All right, I want to look at this function here. So I have a polynomial function, and I want to describe it. I want to see if there's any vertical asymptotes, if there's any horizontal asymptotes, and if there's any slant asymptotes. I also have to know if I have any domain restrictions. So the first thing I do is I look at the denominator and I factor it. Well, it's already factored to a linear form, and so I set those linear forms can equal 0, and so x cannot equal 2. I have a domain restriction on this function. In my domain of f, x can be all real numbers except x cannot equal 2. And that's the domain restriction we get from having x in the denominator. Well, I want to see if there's an asymptote there. So I have to factor the top. And so I'm going to use my AC rule to see if this is factorable. I don't know if it's factorable or not, but I get 4. I get negative 4 to be precise. So A times C is negative 4. And my factors of negative 4 are 1 and negative 4, 2 and negative 2, 2 and negative 2 again, and negative 4 and 1. Well, none of these add up to 5, right? That adds up to negative 3, that adds up to 0, and that, whoops, that's negative 3. 1 times negative 4, yep, negative 3, negative 4 and 1, negative 3, yep. I got my signs backwards here. I apologize. Let me fix my last set of signs here. That should be 4 and negative 1, right? And so 4 and negative 1 add up to 3. That adds up to 0. That adds up to negative 3. But none of them add up to the 5. So this doesn't factor. It's prime. So this is the simplified form. So I'll rewrite my simplified form of this here. And this says I have a vertical asymptote at x equals 2. Because in my simplified form, anything in the denominator that makes the denominator equal 0 will be a vertical asymptote. All right, now I need to check for horizontal asymptotes. So I look at the degree of my numerator and the degree of my denominator. The degree of the numerator is greater than the degree of the denominator. And if we jump to the rules on page, where was it? My page numbers are on here. Page 327, this is going to say that there are no horizontal asymptotes. So the horizontal asymptotes, there are none. Notice how I'm going through each of the rules that we've talked about for each of these. All right, so if there's no horizontal asymptotes, we have to check if there's a slant asymptote. So I have to do this long division out now. I'm going to go through the long division a little quick. All right, so 2x is the thing we need from the leading coefficients. If I multiply it back through, I get 2x squared minus 4x. I'll change my signs. I do like changing color for signs. Makes it so much easier. I remember when doing this in pencil and never, what was I? Did I start with a plus and I changed it to a negative? Or did I start with a negative and change it to a plus? This makes it nice. Those cancel out. That gives me negative x minus 2. So that's telling me I need a negative 1 here. Negative 1 comes through, gives me negative x plus 2. Change my signs. That becomes a positive. That becomes a negative. So I'm left with a negative 4. But the thing I'm interested in is, does indeed look like I have a slant asymptote. And it looks like I have a slant asymptote with a line of 2x minus 1. Because my quotient is 2x minus 1. So what I did is I went through each of the asymptotes and I checked for them. Well, let's look at this on the graph and see if these things appear for us. So let me switch over to graph mode. Hey, that worked good. And my initial equation, my initial function was 2x squared minus 5x minus 2. And I divided that by x minus 2. And we said we had a vertical asymptote at x equals 2. And we said we had a slant asymptote at y equals 2x, what was it, 2x minus 1. Well, let's look at what happens here. I'm going to change my asymptotes to dotted lines. All right, so the green line is my function, and I have a vertical asymptote at y equals 2, and I do. As I zoom out, right, they're approaching y equals 2, and if I approach from the negative side, it zooms off to positive infinity when I get close to 2. If I approach from the positive side, I zoom off to negative infinity as I get closer to 2. But if I go out towards infinity, this green function is definitely approaching the line y equals 2x minus 1. And so we have found the asymptotic behavior for this rational function. All right, let's look at one more here, and we'll do all our asymptote checks on it, and we'll go from there. I'll switch back to the Blackboard thing. That's working there. This will be our last one, and we'll do the same type of checks on it, and we'll look for each type of behavior. I'm actually going to pick one I haven't done before. A small chance I might make a mistake, and that's kind of what I'm hoping for, because I want to show how you can correct things. But I know I already made one where I had a small, didn't have the exponent right when I put it on the graph. All right, I'll read out the function here in a second. All right, so we have f of x equals 2x plus 1 divided by x squared plus 6x plus 8. So this meets the criteria for a rational function. It has a polynomial upstairs and a polynomial downstairs. So the first thing we want to do is find any domain restrictions. So we want to find the roots of this bottom part. And so if I factor x squared plus 6x plus 8, and I set it not equal to 0, I think we'll find that we have x plus 4 and x plus 2 not equal to 0, right? X squared, 4x plus 2x gives me the 6x and an 8. So x plus 4 can't equal 0, and x plus 2 can't equal 0. So my domain for this function has x existing in all real numbers, but x can't equal 2 or 4. That does not mean that these are guaranteed to be vertical asymptotes. I have to simplify my function into simplified form. Thankfully, the upstairs, 2x plus 1 over x plus 4 and x plus 2, well, the upstairs is already factored to its lowest form. And so, hey, these will be vertical asymptotes. So I have a vertical asymptote where these equals 0. And what did I forget? These have negative signs. Told you I was going to make a mistake. I just didn't expect it to be the sign, right? Because I subtract 4 to both sides, so x can't equal negative 4, and x can't equal negative 2. Right? So x can't be negative 2, negative 4. So we have a vertical asymptotes at x equals negative 2 and x equals negative 4. All right, that's not too bad. Now we have to determine if there's any horizontal asymptotes. So again, our rule for horizontal asymptotes says, hey, we look at the degree of the numerator and the degree of the denominator. And if they are the same, the leading coefficients determine the horizontal asymptote. But if the denominator is bigger, than the numerator, then in our horizontal asymptote is y equals 0. So we've got a horizontal asymptote. Now I'm going to say I can't divide this into this. I'm not going to get a quotient and a remainder. So my slant asymptote should be none. And what you will find is if you have a horizontal, you won't have a slant. Right? You can get one or the other of these. All right, well, let's graph this and see what it looks like and see if all those things appear. So let me see if I can get you guys to the graph. Over to the graph, down to the graph. All right, so what did we say? X couldn't equal negative 2, and x couldn't equal negative 4. So we'll put our two asymptotes in there. And then our function itself, we also said there was a horizontal asymptote at y equals 0. So I'm putting all my asymptotes in. Sure, okay, you are seeing the graph, that's good. And so what was my graph on my initial function? As I flip over here, so what happens when you turn a page to quote a page number? Where were we here? We were at 2x plus 1 upstairs. 2x plus 1 divided by x squared. X squared plus 6x plus 8. All right, so I'm going to zoom back in and notice we found our asymptotes fairly well. We have these areas where it runs off towards negative infinity and positive infinity, and we have our horizontal asymptote, even though it jumps up above it. And one of the things that happens if you have to graph these things by hand, is you can find test points that will tell you if you're going off towards negative or positive infinity. But for right now, I want you to use Desmos as your thing to help you find the points and come through. This utility is very nice. It helps us graph things fairly quickly, And it helps us find these pieces. And finding these pieces will help. And so this is what we mean by asymptotic behavior. And if this was a function I was working with, and my range of stuff was between this -4 and -2, I know I'd only be getting this part of the curve. I'd only be getting these positive values. And if I was greater than 2, I know as I get closer and closer to infinity, the value of my function gets closer and closer to 0. And so these are the things we want to pay attention to when looking for asymptotes. All right, so we're coming up on 7:20. At 10 of 8, I'm going to restart the second part, and we're going to start looking at Chapter 5, Function Algebra. I want you to appreciate, I said this on the last lecture, and I kind of, when we said we're going to do 4, 6, and then move into function algebra, the rational functions are hinting at us that we can divide one polynomial by another polynomial. What we're going to want to do is we're going to want to divide any function by another function. We're going to want to multiply any function by another function. We're going to add functions, subtract functions. And that's actually very, very useful because functions can be separate things. And so that's what we're going to come back for. But get something to eat. I need to grab something to drink, take a small restroom break, stretch a little bit, clear the brain out, and I'll start a new stream and send it out around 10 of 8. All right? Talk to you shortly.